now we really will try to prove this, or at least, I mean, go in the direction of proving it. And so, I mean, yeah, we proved Marchenko-Pastur by, yeah, looking on the resolvent, and then somehow, I mean, essentially checked what happens if I'm leaving out one column, one of my data vector, and tried to connect what I had before and afterwards in terms of the Cauchy transform, Stieltjes transform. Okay, and now I want to present a different approach by using the resolvent, which is maybe more suited for doing generalizations in the direction which we wanted here. Okay, I mean, Marchenko-Pastur, even Marchenko-Pastur in its original form, we only proved it for the situation when the entries have a Gaussian distribution. I told you it's still true if the entries are still independent but have a different distribution, and so it would be good to have tools maybe where one sees directly, I mean, what gives me independence and what do I need from the distribution. And then, of course, if I go to the product and the non-linearities, I have to even go further with my tools. I have to go quite far away from what I started. But in principle, I should have a good approach which can be extended to more general situations. And that's what I want to present in the following. So today, I want to give you just another proof of Marchenko-Pastur. And then next time or so, we will extend the methods in this proof such that we can also attack the situation which we have here. Okay, so I mean the theorem can now go, or maybe other questions for this. So we come back, and I mean hopefully I will be able to at least give you some ideas how you get this equation. But today I just want to give you again ideas how you get the Marchenko-Pastur equation. Okay, so I will give another proof of the Marchenko-Pastur law, and this will actually be by using again a specific property of the Gauss distribution, which goes under the name of Stein's identity, and this can be extended going away from Gauss distribution by a cumulant expansion. Okay, so today we will first use this Stein's identity, Stein's lemma, to see how we can get Marchenko-Pastur. Good, and so we look on X, our standard Gaussian random matrix. So this is in R P times N. Now we are not looking at a product at the moment, but only on one of them, going back to really Marchenko-Pastur. So this is our standard Gaussian matrix. Standard Gaussian matrix. So this means all the entries are independent and each entry has a Gauss distribution of variance 1. And we want to calculate the Stieltjes transform in the limit. And of course the limit, so we consider is that both P and N go to infinity such that the ratio P divided by N goes to gamma. And gamma was number between 0 or 1. I mean, just for deriving the equation, I mean, it doesn't really matter. It can be also bigger than 1. Okay, and so what is the Stieltjes transform? So we want to derive an asymptotic equation for the Stieltjes transform. So the Stieltjes transform of, so what is it? Let me call it A. That's what we really want. So this is 1 divided by N X transpose. That's our Wishart matrix. Before I called it sigma hat, but okay. Hats are not very useful in this context here, so let me call it A. And then the Stieltjes transform of A, so this is S of Z. So the Stieltjes transform is the expectation of the normalized trace of the resolvent. So the resolvent is 1 over N of, let me write it, X transpose, so it's this A here, minus Z times the identity matrix. And here we are in P by P matrices, so it's the identity matrix there. I take the inverse of this, I take the trace of this inverse, and then I take the expectation. That's a Stieltjes transform, which of course depends on N and P, and of course we want to see in the limit what we get for this. Good. Okay. And so in particular, you see, what I have here, that's the resolvent of this guy here. So maybe let me give a notation to this, because we will really calculate with this. So R of Z, so that's essentially the Stieltjes transform, but without the tracer and without the expectation. So that's just the resolvent of my operator. So this is, okay, the operator here is A minus Z times the identity to the minus 1. Good. Okay, and so the Stieltjes transform is just the expectation and the trace of the resolvent. So S of Z, this is a function in complex numbers, so this is the expectation of the normalized trace of the resolvent. And now I want to derive an equation, and for this we start from the fact, okay, that the resolvent is the resolvent is the inverse of this, and we just write down what this means. So of course this means that A minus Z times the identity times the resolvent is equal to 1. This is just what it means, that this guy is the inverse of this. Okay, but of course we can multiply this now out. So this means, of course, that let me start from this side. So the identity plus, and then here I get Z times the resolvent. Let me bring this on the other side, which is now this side. Z times R of Z. So this is A times R of Z. Okay, so this is just writing down the relation between A and the resolvent. And now I can, of course, apply the trace and the expectation. And of course, here I get my Stieltjes transform. The problem is this term. Okay, but still, let us see what we get. So if I apply the trace and the expectation, so the normalized trace of the identity matrix is 1, expectation is also 1, so here I get 1. Then the Z is just a number, this comes out, and the expectation and the trace of this guy is my Stieltjes transform. So that's good. So here I have my Stieltjes transform. And maybe you remember that our equations were always of the form 1 plus Z times the Stieltjes transform, and then it was a mess on the other side. And now you see, the mess on the other side is somehow finding out what this thing is doing. But in principle, what I have here is the expectation of the trace of A times R of Z. Okay, and of course this is not directly clear how this is related to the Stieltjes transform. Without the A it would be the Stieltjes transform, but multiplying with this A, this is something which we have to control. So okay, and so maybe let me write this down a bit more, working it out. What this is, maybe, I have here a matrix product, and this A actually, let me write it down. So I have, so this A is x transpose divided by n, so let me write the 1 over n here. And then maybe the normalized trace, if I'm doing explicit calculations in terms of my matrix entries, it's better to go to the unnormalized trace. So let me write this here as the unnormalized trace, but the normalized trace is the unnormalized trace divided by the dimension, and here I'm in p by p matrices. So I have to divide by 1 over p, and then I have here the expectation. Here I have the unnormalized trace, and now I have here x transpose times R of Z. So this A here is x transpose divided by n, and this trace divided by p is this normalized trace. Okay, and now so what I have here is now the product of matrices, and I want to split off this one x here. X is really a matrix of which we know the best what it does, because the entries are independent Gaussians. Okay, so at some point I have to use this information. What do I know about my basic matrix? The basic matrix is X. So I write this as 1 n divided by p, and then I write this here. Okay, so this is a matrix product of X times this matrix, and then I'm also taking the trace. And now I write this in terms of the entries of what I have here. So I'm writing this as I'm summing over i's from 1 up to p, and from j over j from 1 up to n. And I have the expectation. And okay, so I take here the xij, so that's the ij entry of the matrix X, and then I'm multiplying it with the corresponding entry of what I have here, so xt and r of z. I'm not splitting this at the moment, and I take there the ji entry. So I'm summing over I and j. Summation over j is the matrix product between this and this, and summing over the I here is taking the trace. So that's just writing this out explicitly. And of course the I is running from 1 to p, and the j is running from 1 to n, because that's the size of our matrices. Good, so and now you see what I have here, and what I should understand if I want to go further is the expectation where I have one of the entries of my matrix X, so this is a Gaussian entry, multiplied with something here, and this something here, this is now a function of my matrix X, of all the entries. So this here, I mean, this is the ji entry of the matrix X transpose times the resolvent. X transpose is easy, but the resolvent, of course, is a more complicated thing. But nevertheless, what I have here is a function of all the matrix entries of the matrix X. So this is a function of all xkl, the entries of X. Okay, and I mean, it's not clear why I'm saying that. Is this useful? So what I have here is the expectation of a Gaussian random variable times a function of this variable and others which are independent. Okay, and that's exactly where Stein's identity happens, because this tells me that one can reformulate such a situation where I take the expectation, or let's say I have independent Gaussians. That's what I have here. The entries of my X matrix are independent Gaussians, and so I can somehow rewrite the expectation of taking one of these Gaussians and multiplying it with a function of all of them, and what I get is actually the expectation of the derivative. That's Stein's identity. And this will then be useful later. But so let us first look on this. So that's the main tool we are using here, Stein's identity, or maybe sometimes Stein's lemma. And this again is something very simple. So it's nothing really complicated or so. It's simple, but it's very useful. Okay, and so I mean, let me now denote my independent Gaussian random variables by t1 up to tk. I mean, here they are indexed by the double index because they are collected in a matrix, but this doesn't play a role. It's just that I have a collection of independent Gaussians, and I multiply one of them with a function of all of them. So let me call the Gaussians, let's say t1 up to tk. So this should be independent, let's say standard Gaussians. If they have a variance, of course I will have the variance showing up in the formula, but the xij's in our case are also standard. So let's stay with this, independent standard Gaussian random variables. Okay, and then I consider a function. I mean, this in our case, this would be this function. Let me just call it h. So it's a function where I can plug in all my variables. So I have k of them in this case. So it's from rk to r. So this should be a nice function. And this essentially means that what I write down in the following should make sense. So, I mean, for example, it should be a continuously differentiable function such that partial derivatives are of polynomial growth. Okay, but anyhow, so then we have for all I from 1 up to k that if I now look on the expectation of such a form where I'm multiplying with one of my variables the function of all of my variables, that under the expectation I can rewrite this by essentially getting rid of this variable and the price I have to pay for this, that I take the derivative of this function with respect to this variable. So what I get here, this is the same as the expectation of the ith partial derivative of h of my variables, t1 up to tk. And this is the partial derivative. I mean, this is a function of k variables, and I take the partial derivative with respect to the ith variable. And I mean, here I'm multiplying with ti. So if I'm multiplying with t1, then I take the derivative with respect to the first variable. If I'm multiplying here with t2, then I take the derivative with respect to the second one. Good. Okay. So this is really very nice, and I mean it's very simple, and it's essentially just the property of the Gauss distribution. That if you take the Gauss, if you take the derivative of the Gaussian density, you get down a factor t. And this here is essentially going the other way via partial integration. So the proof of this is just doing partial integration, and essentially we are here in the k-dimensional, so we have to integrate with respect to the product of our Gaussian densities, but the main thing happens in the direction I. So in principle it's enough. The main thing happens if I just do it for k equal to 1. So for k equal to 1, it's just partial integration. Ice is smooth differentiable, or maybe I should say, for example, so nice e.g. So what is in any case good enough? It should be continuously differentiable, such that the function and all its partial derivatives are at polynomial growth for going to infinity. They are not growing too fast at infinity, which means essentially the exponential function e to the minus t squared goes faster to 0 than they go to infinity, so that boundary terms don't play a role. Continuous differentiable with polynomial growth at plus minus infinity. So it is essentially in the partial integration you have to guarantee that the boundary terms don't play a role. Okay, but maybe let us look on this. So I mean, so in a one-dimensional case I have just one variable. So I have t, and then I'm multiplying with a function of t. And what is this? So this, of course, is this expectation is with respect to the distribution of this, which is the Gauss distribution. So what I have here is t times h of t, and I have to integrate with respect to the e to the minus t squared over 2 dt times 1 over square root of 2 pi. So this is just, I'm integrating this thing with respect to the Gauss distribution. Okay, and now the point is that this t here, I can put it to this density, and then I just have the derivative of this density. That's the main thing here. The property of this Gaussian density is that if I take the derivative, I get out a factor t, because the inner derivative, of course, of this t squared over 2 is just t. So maybe I write this as 1 over the square root of 2 pi integral. Let me write it like this: h of t times e to the minus t squared over 2 dt. And this guy here, this is just the derivative of e to the minus t squared over 2. And now you see I have an integral. This is the derivative of this. I'm integrating a function times the derivative of another function, and then partial integration tells me that I can reverse the order. Instead, I can also take the derivative of this times the function here, and then I get boundary terms. And these boundary terms better should be 0. And this is guaranteed if this function h, it might go to infinity, but it should not go faster to infinity than this guy here goes to 0. So I mean, this goes exponentially fast to 0. So if I allow, for example, polynomial growth here, that's still okay. So I mean, that should be the assumptions which I have there. And of course, my function should be differentiable. Because otherwise, I mean, of course, the statement doesn't make sense. Okay, so this here, this is the same with partial integration, I get a minus sign. Of course, I also get a minus sign from here. Okay, because I don't want a minus sign in my statement. So this here actually is okay, minus this. The derivative of this is this here, because the inner derivatives also give me a minus sign. Okay, so and then the partial integration gives me another minus sign, which cancels this minus sign here. So what I get here is then plus 1 over 2 pi, and then I integrate the other order, namely I take the derivative of h, and I take here not the derivative of this function, but I take this function e to the minus t squared over 2. And the minus sign has cancelled the minus sign here, dt. And now you see I'm still doing a Gaussian integration, because I still integrate with respect to the Gauss distribution, but now I'm integrating the derivative. And of course, I get boundary terms. I mean, the boundary terms, yeah, so what are they? Maybe I write them also. There I should take the product of my functions at the limit plus and minus infinity. So I should take the function h of t and e to the minus t squared over 2, maybe with a minus sign, but at plus and minus infinity. Okay, and then this here goes fast to 0, and if this doesn't go too fast to infinity, then those boundary terms are 0. So those guys, I mean, that's mainly the assumption which I need on my h, that those boundary terms are 0. So this is 0 by my assumption on h. Okay, yeah, and then of course this here, this is now just the expectation over this function h prime of t, with respect still to the Gaussian distribution. Yeah, okay, and I mean if I have a general k, not k equal to 1, then I just do the partial integration for the ith coordinate, and the other integrals, they don't play a role. Because I mean I have here really, I'm integrating with respect to the density of a standard Gaussian vector in R to the k, which means the density is just the product of the one-dimensional densities. And so I just have iterated integration with all those densities, and then I just do the partial integration for the ith coordinate, and the other things are not affected. And of course then I just do get here the partial derivative with respect to the ith coordinate. So for general k, do partial integration for the ith coordinate. Okay, good. So this Stein's lemma is really quite easy statement, but it is really very useful. I mean, it can be used in the following, in particular in our setting, because now we can go back to what we have here, and now I have a situation like this. I have a collection of independent Gaussian variables, the entries of my matrix X, and here I have the expectation where I multiply one of those variables with a function of another. And then this tells me, instead of multiplying this, I can also take the derivative of this guy with respect to this variable. Okay, and of course now I have to try to understand what is the derivative of this thing. But I mean, okay, this is clear, and the resolvent is essentially the inverse of something, and taking derivatives of inverses is also not too complicated. So I mean, this is really where we can write down kind of concrete formulas. Good, okay, but we have to go back to this and see what we get there. Yeah. So let us see. So what we need here is the expectation of one of the entries of my matrix, the xij, and I mean I need this for all I and j. So I mean, but let us look fixing I and j, and let us look what we get there. I have xij, and then I have to multiply with the ji entry of the matrix xt and R of Z, Ji. Good. So what is this? So, okay, yeah. Okay, so I'm using square brackets for too many things. Huh? So, okay, so maybe here I'm taking the expectation of this. And I mean, if I'm writing like this, I mean, this is a matrix with the square bracket, putting something here. This means I take the Ji entry of this matrix. Huh? Okay, and of course the, yeah. Okay, and now of course, so I have, okay, so this is by this Stein's identity, this is the expectation of, instead of multiplying, I take now the derivative. And I have to take the derivative with respect to this variable. So it's a variable ij. So, I mean, I write this as delta ij. So this should mean it's a derivative with respect to the variable xij. Of this thing here, so which is x transpose R of Z, the Ji entry. Good. Okay, and of course, I mean, I have here now a product of two functions. I mean, I have here just the transpose of the matrix, which of course is very easy to take the derivative, and I have here the resolvent, which is a bit more complicated. But of course, I use now essentially the product rule. So the derivative of this is just the derivative of this times this plus the other way around. And for this, yeah, again, I mean, this matrix product, I should write it in terms of coordinates, because I mean, I would like to see the entries. So this guy here, so this is the Ji entry of this product of my two matrices. So this is of course just the matrix product. So this is the matrix xt, the transpose of this, and I take the J entry, and then I'm summing over k, because I do matrix multiplication. I'm summing over k from 1 up. Okay, yeah. So this is x transpose. So x is a p times n matrix. So x transpose is a n times p. So this means the k has to run up to p, and then I'm multiplying this with the corresponding entry of this matrix. So here the k entry, and here the I entry. Or this is just writing down matrix multiplication in explicit way. And of course, I mean, what is the JK entry of the transpose of the matrix X? This, of course, is just the KJ entry of X, but this is just our variable XKJ. XJK, yeah. Okay, so this here is really just one of the variables, and here this is, of course, more complicated. Yeah. Okay, but now I take the derivative of this, and now I apply the product rule. And for this, it's very easy, because that's just, it's either the variable I want, or it's one of the other variables, and then the partial derivative is 0, and then I have to take this. Yeah, so what do I have? I have the expectation of, yeah, so, and I put this sum here, I'm taking out. Yeah, it's a sum k from 1 up to p. Okay, and then I take the derivative of this. I take the product rule. So I take the derivative of the first guy. So it's a derivative with respect to the ij variable of the kj variable multiplied with r of z ki variable plus, okay, and then the product rule. I mean, I just get I mean, this sum here applies to both of them. So I get the first variable, xkj, but then I have to multiply it with the derivative of the second function, derivative with respect to the ij variable of r of z ki. Okay, and then all brackets closed. Good, and now let us see what we have. And of course, the first term is very easy. I mean, what is the derivative of the kj variable with respect to the ij variable? I mean, it's just 1 if this is the same as this, and it's 0 otherwise. It's a partial derivative of, if I have variables, I mean, okay, I just get the delta. So this means this I has to be equal to k, and this j has to be equal to j, which is the case. Okay, so the condition is that I has to be equal to k, which means in the summation over k, actually I only have to keep the k equal to I component. Good. Okay, and so maybe I write it here. This is delta ik, and then I can continue here. So the first term, this is the expectation of, and now you see this here, this here just tells me that the sum only keeps the term k equal to I, so the sum is gone over k, and I just have the term where k is equal to I. So I have just here r of z, and of this I take the I entry. Okay, and it is of course a good thing, because you see, I mean, I'm still summing over I, which will give the trace of this thing. That's a thing which I really want. The trace of the resolvent and the expectation, that's my Stieltjes transform. This is a good term, which I can deal with later. But of course I have the other terms, which make more work. So what do I have there? I mean, there I still have, so for this term, I still have my sum from 1 up to p. And then I have the expectation of x kj, the derivative of ij of r of z ki. Okay, good. So that's what I get. So this term is easy, it's dealt with, and here I'm still left with this. And now you see what I now need is that I have to take the derivative with respect to one of the x's of my resolvent. Okay, and that's something which one can also calculate, and actually you are asked to do this in the assignment. So namely what one has, this is in the new assignment, that if I take the ij derivative of the resolvent of KL, I mean, here you see I have here ij, and here actually I have ki. So this index is the same as this, but maybe it's better not to get confused, and maybe it's better anyhow just to have here arbitrary indices. So I take the KL entry of my resolvent, and I take the derivative with respect to the ij variable. Okay, and that's can be done. So namely this is minus 1 over n times the resolvent of z, ki entry times the x transpose r of z jl entry plus r of z times x kj entry and r of z il. Okay, good. So that's what you are asked to prove in the assignment. And I mean, maybe this looks, I don't know, maybe a bit strange at the beginning, but I mean that you should get something like this. Maybe it's not so surprising. I mean, because the R transform is 1 over. So maybe just, I mean, R of z is actually, let me write it as 1 over x transpose. Maybe you have a 1 over n, which, okay, is this minus z times the identity. Okay, and if you take the derivative of, I mean, you take the derivative with respect to the variables which are sitting here. And if you take the derivative of 1 over, you get 1 over squared. You get it twice, which means that you get the r here actually twice. So essentially, I mean, the derivative of 1 over x is 1 over x squared, and actually minus. So you also see a minus here. And then you have to take the inner derivatives. So you take the derivative of this guy here, and this is a squared thing. So if you take the derivative of this, 1x will survive, either an x or an x transpose, and you see they are showing up here. And but of course you have matrices here, so the order plays a role. So you have to put the x between the two r's here. Okay, so but the structure of this formula shouldn't be too surprising. It's just that one has to be carefully that one really gets all the indices here right. But in principle, this is just a easy exercise in doing partial integration of a partial differentiation of the inverse function. Good. Okay, but so this is something which is true and can be used. So we can use it here, and so we have more or less this structure. The only point is that we have here the I is appearing twice. So what is here, the L, is actually also an I. So I'm using now this formula where this L here actually is also an I, because that's what I have there. So this here is an I, and this here is an I. So I'm using this formula. I mean, this here is true for all I, J, K, and L. So in particular, if L is equal to I. Good. So I have this, and so yeah, this term here is now the following. So I have the expectation of xij delta ij r of z, the ki entry of this. So this is, yeah, I mean just using this formula, but just L equal to I. Expectation of this. This is, yeah, I have the minus 1 over n. I have the expectation, and I'm multiplying it here still with xij, and then I'm using this formula. So I have no, I have here xkj. Okay, so xkj. I have here the xkj, and then I have this thing here. So this is the sum of two terms. The first is r of z, ki times x transpose r of z j, and the L is now an I, so ji, plus, okay, I still have this x k j, and I have to multiply it with the second term here, so r of z x, the k j entry, r of z, the I entry. Okay, so, and maybe again this expectation, let me denote it with a round bracket, take the expectation of everything. Yeah, okay, and so maybe now let me go back to what I really want. I mean, this is only part of what I want. So what I really have is this equation 1 plus z times s of z. So let me write this 1 plus z times s of z. So what was this? So this was this 1 over n times p, and then I have this double sum. It's 1 over np. This double sum, where I is running from 1 up to p and j is running from 1 up to n. Yeah, and then I have this expectation which I treated there, and I get this first term, which was the easy term. So this was just the expectation of r of z I. Okay, so that was easy. And then I have this term here, which I treated here. And this is still something which is not so clear at the moment. So I get here this guy here. So minus 1 over n. And actually there I still have the summation over k. In the first term the summation over k is gone because I had a delta function there. But for the second term, for this term, I'm still summing over k. So minus the sum over k, and k is running from 1 up to p. Yeah, and I have a 1 over n coming from here. And you see, I mean, essentially, I mean, I have 3 summations, and I also dividing by the guys which go to infinity. So there's a chance that asymptotically something survives, because I'm summing over terms, and I mean all the terms, if they are of the same order, I should divide by them to get something in the limit. So that's good. 3 sums, and I'm dividing by 3 times these numbers which go to infinity. Good. Okay, so I have this minus 1 over n, the sum, and then I have this expectation here. So I have this expectation of x k j r of set ki. Okay, it's writing the same things again and again, but okay. I mean, this is really something you have to do for yourself, in particular just to get the indices right, because in the end everything has to fit together. It's something like this, but if you don't get the indices right, then okay, you cannot be sure. Okay, so this is this plus the second term, x k j r of set times x k j times r of set, the I entry. Good. Okay. And so, yeah. So I take this. Okay, and now you see I have here essentially 3 terms. I mean, I have this term, and then in this sum here, I have also 2 terms, and I write this as 1 minus 2a and minus 2b. And we have to now to look separately on those terms and to understand them. And it is clear that this term is easy. And so maybe, maybe I still do this because this is more or less clear. And then maybe next time I continue with the other ones because there's still some work. I mean, we are getting closer to, I mean, in the end we have to express everything with the Stieltjes transform. Okay, and we're getting closer to it, but it's still not so clear. I mean, the expectation of the trace of the resolvent is the Stieltjes transform, but we have x's in between. And so, I mean, this of course changes it somehow, and we have to get rid of them somehow. And I mean, here you see that's what we want. And so maybe let me do this term, and maybe also just to see that really asymptotically we get something. So we still have the sums, but we also divide by n and p, and this really fits together nicely. Okay, so what is 1? Let me just write it down again. 1. So this is still, I have the 1 divided by n and p, and I have still 2 sums. I have the sum over I and j. And so let me write the sum over j at the outside. So this is running from 1 up to n. Okay, and then I have the expectation of, and the sum over I bring inside. So here I'm writing, now I'm summing here over I from 1 to p, and then I have here the resolvent of set, the I entry. Yeah. Okay, and now you see, I mean, this summation fits together with this. This is just a trace. So this is the unnormalized trace of R of set. I mean, R of set is a matrix. Okay, and of what size? I mean, R of set is the resolvent of x transpose, and this is a p times p matrix. So this is a p times p matrix. So if I want to normalize it to the unnormalized to the normalized trace, I get a factor p. So this is p times the normalized trace of R of z. And now you see, I mean, this p goes nicely with this 1 over p. And then we are summing here over j, but this result here doesn't depend on j, so I just get n times the same result. So what I get is actually I have this 1 over n here, but then I get n times the expectation of the trace of the resolvent. Yeah, and the trace of the expectation of the normalized trace of the resolvent, that's the Stieltjes transform. Here, I mean, this here goes away, and so what I have here is really just the Stieltjes transform. Okay, so this is good. I mean, I get here 1 plus z times the Stieltjes transform is, and this term gives me just again the Stieltjes transform, which is one component in the equation which we are going to prove in the end. But there are more things in my Marchenko-Pastur. But this is already okay. But we have to check. So this here, this is okay. We have done this, but we have to see what happens with those terms, and they are still not so easy as this one. We still have to work a little bit with them. Good. Okay, but next time I will come back to this, and we will check that indeed it works and really gives us the equation for the Stieltjes transform of Marchenko-Pastur. Good. Okay, but I think that was enough for today. We need some rest, and next time we finish this. Okay, thanks. Yeah, let us first look on this one. So let me write it down again. So 2a. So what is this? So I have here, okay, I have here my sums. Okay, I have 1 over n, 1 over p, and another 1 over n. So I have altogether a 1 over n squared p. Okay, and then I'm doing kind of matrix multiplication here. I mean, I'm summing over the indices. I'm summing over all of them. I have I, j, and k. And here, you see, this is the matrix x, kj. Okay, so if I combine it with this one, so it means I'm multiplying x with this matrix. And then here, you see here the indices are in the wrong way, so I should take the transpose of this. So I multiply this matrix with this matrix, and then times the transpose of this. And the summation over all the indices gives me the matrix multiplication, and I'm summing also over k, which gives me the trace. Okay, so what I have is then actually the expectation of the ordinary trace of, and then I have to multiply things in the right order. So let's say I start here. This is the matrix X. Then I continue here because I have here j. This fits together. Then I multiply it with this, and then I have the I. So I should have the I here at the first position, which means I take the transpose of this. And then I have here the k at the end, which fits with the k here, which is the effect of the trace. So I have here the multiplication of x, then the xt r set, and then the transpose of this other resolvent, r set transpose. Good. Okay. And now you see, I mean, my summations are now all gone, and I have divided by those guys. Okay. And I mean, 2 of them are okay because I have here the unnormalized trace. I should normalize this to have the normalized one, which means I should divide it by, by what? So which matrices are this? So X is a P. Let me see. This is here now. This should be a P times P matrix. Okay, so I should take this P for normalizing this trace. I think this is, X is a P times N matrix. Good. Okay. So and then of course the X transpose, this should also be divided by N, because that's the quantity which has a limit. Okay, so we use this P for changing this to the normalized trace, and we use one of the N's for getting here something which has an asymptotic limit, but actually then we are left with an extra 1 over N, which in the end says that this term actually goes to 0 in the limit. Okay, so we have the 1 over N, and then I have the expectation. This I change into the normalized trace, and here I write X transpose divided by N. And here I have just those guys, but they are in the right scaling, so they have a limit. Okay, so in principle, those are guys which asymptotically have a limit. Okay, but then dividing by 1 over N, this means asymptotically this goes to 0. So this actually is a term which disappears in the limit. Okay, so it's complicated, but maybe we wouldn't know directly what to do with it, but fortunately we don't have to know what to do because it just goes to 0. Okay, so the main ingredient which survives will be the other term. And you see why this somehow survives, because this here has a nice trace structure. So it's actually now, it's not a product of 3 matrices and then taking a trace, but we have here one trace, and then we have a product of two other matrices, which means this will survive in the limit. Good, but okay, let me write it down. So this term 2b. So what is this? So this is 1 over n squared p. And then I have the expectation. Yeah, and let me distribute the summations to where they belong. So let me say I have here the sum k from 1 up to p, and the sum j from 1 up to n. And then I have the xkj are set x, and of this I have the kj entry. And then I'm left with the last term, which only involves I, so I do the summation over I now here. The summation over I is running from 1 up to p of R set the II entry. Okay, so that's what I have here. And now, of course, this summation here, this is just a trace of this matrix. Okay, so this only involves I, the other indices are not there, so this is just a trace of R of Z. So I can take this out, or yeah, okay, I can take it out of this sum. And in this sum, of course, I'm also again doing the trace and the matrix multiplication. Again, it's just that the indices, I mean, one of them should be reversed. Yeah, let me say, I mean, I take the transpose of this, because then I have here jk, and then this fits together with the kj. So I multiply the transpose of this with this matrix, and then I'm taking the trace. So this thing here, this is the trace of the transpose of this, so that I get the indices reversed, and then times this matrix R set X. Okay, and now you see that, hopefully, that now I really need all those divisions. So I mean, I have two traces, which I should change to a normalized trace. So I need an n and a p for this. So this here is a p times p matrix. So here I need the 1 over p. This here is a n times n matrix, so I need the 1 over n. And the remaining 1 over n essentially goes to this guy here. Yeah. Okay. Or maybe it's even better to really move this x here to the beginning, because then we get back our x times x transpose. That's actually the operator, the matrix in which we are really interested. So this here is actually the trace of x transpose R of Z. This guy here. Okay, and now you see I use maybe let me write it again. So I have the expectation, and then I'm changing this unnormalized trace. I change to the normalized trace by dividing it by 1 over p. So this gives me then the trace of R of Z. Okay, and here, yeah, I'm putting a 1 over n together with this trace, and I'm putting here a 1 over n with this. Okay. And so this here is now the unnormalized trace, and now I have quantities which all have a limit. So this is really something which survives in the limit, and which we can essentially also recognize what it is in the limit. No, you have to be careful here. I mean, I have a 1 over n here. Okay, but actually, so what size of the matrix is this? So this is x transpose. So this is a p by p matrix. So actually, to change this to the unnormalized trace, I need the factor p. So this here, this trace is p times the unnormalized trace. And so you see now I get the ratio p over n, which is our gamma, which is good, because this should also appear somewhere in our equations. So it's the ratio of the sizes. Yeah, okay. And so, what do we have? So I mean, this here, this again is our Stieltjes transform. That's good. Okay, and this here, okay, so this, without this, it would be the Stieltjes transform. But now you see, this is essentially the same thing from which we started in our calculation. This is namely this here, which we know it is 1 plus z times the Stieltjes transform. So what we did, we started with 1 plus z times the Stieltjes transform, got this term, and then we calculated this term, and in the end we get something back which contains again this term, which we can replace by this. But we get it in such a form that of course we are not just going back everything we did in between, because this is now multiplied with gamma and the other Stieltjes transform. Good. Okay, but in any case, I mean, yeah, this here is by this calculation, and this calculation is just saying that the R transform is the resolvent is just the inverse of this guy, just multiplying it out. So this is quite trivial. So this is just 1 plus z times s of z. Yeah. So we have now identified all the three terms in this equation here, and this is equal to this, the sum of them. So we got our final equation. So this means we started from 1 plus z times s of z, and then we get, after our calculations, the three terms, and the first one was easy. This was just the Stieltjes transform. Then the second disappeared, and the third one is the one which we calculated here. I mean, it has a minus sign. Then we get a gamma from here. Here we have the s of z, and it is multiplied with this 1 plus z times s of z. Okay, so that's the equation which we get here. And again, it's a quadratic equation for the Stieltjes transform, and of course it is the same equation which we got when we did our original proof of Marchenko-Pastur. Okay, just multiply it out. Maybe you write it as in terms of s squared, s, and constant, and then you see it's exactly the same coefficients. So this is the same equation as in our proof, original proof of Marchenko-Pastur, which was theorem 4.2. Okay, so we have now a different proof, which is using different tools. I mean, the general idea is the same. Try to get an equation for the Stieltjes transform, but we did it in a somehow different way.